Burn like a pro.
Have you ever wondered how scientists look at a pile of white powder and know exactly how its atoms are connected? We can't zoom in far enough to see the individual atoms with our bare eyes, so we have to reverse engineer the structure using math. The result of that reverse engineering is something called a molecular formula. Think of it as the true physical, architectural construct of a substance. It is the exact real-life recipe of a single molecule. This image shows exactly what a molecular formula reveals, a complete inventory. Look at the water molecule, H2O. The formula tells us the exact types of elements, hydrogen and oxygen, and the total number of atoms, 2 hydrogens, 1 oxygen, making 3 atoms total. While the molecular formula gives us the literal reality of the substance, a massive blueprint, like magnesium sulfate, with its 6 total atoms, is often too complex to figure out directly from raw, unrefined lab data. Because of that complexity, chemists first look through the empirical formula. If the molecular formula is the actual building, the empirical formula is the simplest base blueprint. It tells us the most basic, stripped-down ratio of the elements present. This diagram shows how an actual, complex molecular construct can be mathematically reduced. Take C4H8. By dividing all the atomic counts by 4, we get down to this bare-bones foundational ratio, CH2. Here is a comparison table showing the relationship between these two formulas. Notice the top row. For water, H2O, the actual ratio of atoms is already in its simplest form. That means the molecular formula and the empirical formula are completely identical. But look at C3H6. Its actual construct is different from its CH2 base blueprint. Discovering this simple empirical base is a required first step in the lab. It provides the proportional building blocks from which all larger chemical structures are scaled. So, if we know the massive, real-world molecule, how do we reliably strip away its scale to find that base blueprint? We use a common factor. This is simply a single number that can evenly divide all the subscripts in a chemical formula. This image illustrates a reduction engine using a divisor funnel. You can see how the common factor extracts the simplest ratio across different scales. For C4H8O2, we divide by 2. For the much larger sugar molecule, C6H12O6, we divide all the subscripts by 6. Finding this common denominator identifies the consistent proportions of the elements. Regardless of the molecule's actual size, dividing by this factor reveals the same foundational ratio every time. Now, what if we are starting from scratch? This diagram outlines a universal 5-step framework. It is the standard forensic toolkit chemists use to reverse engineer formulas from unknown lab samples. Suppose we have a laboratory sample containing 103 grams of lead and 16 grams of oxygen. From these starting weights, we can work backward to determine the compound's structure. This chart breaks down the data entry and conversion phases. In steps 1 and 2, we log the elements and their given masses. Step 3 is the critical conversion. We divide the 103 grams of lead by its AR, or relative atomic mass, which is 207. Then we divide the 16 grams of oxygen by its relative atomic mass of 16. Step 4 normalizes the data. By dividing both results by the smallest numerical value from step 3, which is 0.4976, we force the math into a clean whole number ratio. Lead becomes 1 and oxygen becomes 2. This precise pipeline flawlessly translates chaotic, real-world physical weight into perfect, predictable geometric ratios, yielding the formula PbO2. This flowchart shows the exact same 5-step pipeline, but applied to percentage composition. Whether you start with raw grams or a 34.5% share of iron, the methodology works perfectly to yield a formula like FeCl3. This diagram introduces the expansion loop. Once we have our simple empirical blueprint, our ultimate goal is to scale it back up to build the real physical molecule. This graphic shows how we calculate the exact multiplier. In step 1, we take the given MR, or relative molecular mass of the substance, in this case 180. We divide that by the mass of our simple CH2O blueprint, which is 30. That gives us our multiplier, 6. Moving to step 2, the final assembly phase, we apply that multiplier of 6 to the CH2O base blueprint. This constructs the true molecular formula, C6H12O6. This two-way street, reducing down to analyze a base ratio and scaling back up to assemble the final structure, is the complete cycle chemists use to decode the invisible world. Let's put on the hard hat and act as the architect. We can apply these tools rapidly to 3 quick scenarios. First, we need to find the empirical base of hydrogen peroxide, H2O2. By finding the common factor of 2 and dividing, the subscripts physically split in half, leaving us with a simple base of HO. Next, let's push some raw data through the pipeline: 24 grams of carbon and 6 grams of hydrogen. We divide 24 by carbon's atomic mass of 12 to get 2. We divide 6 by hydrogen's atomic mass of 1 to get 6. Normalizing that 2:6 ratio gives us a base of CH3. Finally, let's scale up that CH3 blueprint using a real-world molecular mass of 30. The CH3 base has a mass of 15. Since 30 divided by 15 is 2, our multiplier is 2. The block duplicates, resulting in C2H6. Internalizing these rapid conversions allows anyone to translate random physical samples into precise, readable chemical maps. This image is the complete stoichiometry master reference guide. It recaps our checklist. The molecular formula is the actual atomic count of a substance, while the empirical formula is its foundational reduced ratio. The common factor and the 5-step pipeline act as the unbreakable mathematical links between visible weight on a scale and the hidden atomic structure. Chemists use these blueprints to map the internal architecture of matter, translating raw weights and percentages into a precise model of the physical world.